Right, so cables subject to distributed loads. I have quite a few learning objectives here on these. Are cables subject to discrete loads, which is what we covered with the video lecture on Friday? Very similar to frames and machines, where it was about identifying all the possible FBDs and then picking an FBD with knowns and not too many unknowns. And so that approach is really great for that. And both of these are really about more practice drawing FBDs and understanding the different ways to use our free body diagrams. On this one, though, we'll actually be deriving some equations from one of those FBDs that we can then apply to a lot of different problems. So our learning objectives, we start with some conceptual stuff. Describe the locations of minimum and maximum tension in a cable that's subject to distributed loads. We'll talk about that. Draw the FBD that allow you to develop these equations. So we have a quadratic, we got a tangent of theta, we got a square root of the sum of the squares equation. We'll talk about where all those come from. We'll derive those. And then we need to be able to use those equations to solve for these cable problems. We'll also talk about, there's 3 other FBDs. We'll talk about those other 3 FBDs and then how we would use those FBDs to solve for these problems and identifying these unknowns and how many unknowns we have and all of that good stuff there. These problems are related to things like the Golden Gate Bridge. And actually, we're going to see our cable problems subject to distributed loads. Our cables have this nice curving shape like we see on the Golden Gate Bridge. However, we are making one major assumption that is not totally valid, and that is to neglect the weight of the actual cable. So we're going to neglect the weight of that curving cable. Changes things drastically. However, those problems are a lot harder. And so we're going to look at just neglecting the weight of that cable and incorporating the load that it's carrying down here. For example, in this one, it would be the bridge deck. And so we'll incorporate the load of that bridge deck there. Clifton Suspension Bridge, another nice example here. This is in England. Look how nice that looks right there. And we get this curving shape again. Now, you might think if these cables are all causing a point load on that cable, that there's actually straight segments in there. Well, they're close enough together, these vertical cables, to transfer the load here uniformly up to that cable. And so we get a nice curving shape across there. So we're also assuming that those cables are close enough together to where we get this nice curving shape on there. Also, the fact that the weight of the cable is on there makes that nice curving shape as well. When we look at pictures that are more similar to what we're going to start seeing in our textbook here, we see that curving shape again, those vertical cables transferring the load from down here up to that cable. We're going to write all this down, but the origin of the coordinate system will always be at the low point on the cable, which is also where the slope of the cable is equal to 0. Now, some of our homework problems, or actually, let me go back here for a second. Now, if we have our supports at the same elevations here, so if A and B are at the same elevations, do you think we can find the location of the origin of our coordinate system? Wouldn't it be exactly halfway from left to right? And in reality, that's going to be something we're going to need to solve for. Like if they put these at the same elevation, we can figure out where that low point is. It's exactly halfway. And we are going to see that on some of our homework problems where the supports are at the same elevation. They tell us this is 6 feet right here. Well, we should know exactly where the low point on that cable is. And so we can locate our coordinate system right there. On other homework problems like this one right here, we do not know. We know it's at the location of 0 slope, but we don't know where point B actually is located. And we're actually gonna have to figure that out before we can solve for anything else, is figure out where is that low point going to be located, which would be very similar in reality, where like we know how far we have to go to get across a river. we might know, oh, there's a good anchorage point at this spot 40 feet above. There's another good anchorage point over here at 20 feet above. But then we have to figure out the rest of that geometry. Next, I want to do a iClicker quiz here. This will be our makeup for, oh, I didn't even stop the other one. Let me stop the other one. Let's do another one here. This will be our makeup for Friday. Where do you think the maximum tension is located? Just intuitive. Let's see where everybody's at. Where do you think it might be? Is it A or B or C? Okay, that's most of us. Let me see what people are thinking. All right, 60% said A. That is the correct answer. It is going to be just like before. It is going to be at the location where the slope is the steepest. So maximum slope is going to give us our maximum tension. So A, and it's always going to be the point that's higher. Whatever point is higher is going to have a steeper slope. So A is higher than C, so it will have a steeper slope. So yeah, get those answers in. And point A, correct answer. Point B, actually where we have zero slope, is actually going to be the minimum tension in our cable. Another interesting thing about these cables is that even though this is all one solid cable, because its slope is changing for each point, its tension is also going to change at each location as well. All the other problems we've done, if we have a cable segment, it has like the same tension throughout that same cable segment. This is all one solid cable, but it's going to have different tensions at every single location here. We will derive here today the equation to express how that is changing. And then our homework problem number 2. Oh, wait, no, that's the one. Oh, wait, we're looking, hang on, getting confused here. Too much going on. All right, our third homework problem, actually in this one, it's got two main differences between the other ones. One, it's got a triangular distributed load, and we never get to the spot where the tension is minimum. We never get to a slope equal to 0. So it's going to be a little bit different with the way we solve it. And I would recommend looking at this Canvas example under the supplementary example problems. It's very similar. It's really, it's just one FBD. So it's not a lot different than what we're going to do today, but take a look at that Canvas example problem number 2 to help you in solving that last problem on cables subject to distributed loads. Okay, let's go ahead and let's start taking some notes here on our cables subject to distributed loads. Let's draw a nice picture here of one of those cables. Why don't we show a support over here, and then this is going to kind of curve down, reach a 0 slope in there, and then let's curve back up, and we'll go to a support on the other side that has a higher elevation. We can call this point over here point A. This point over here can be point B. We will have those vertical cables that'll attach down here to whatever we're supporting. Draw some thin or dashed lines there, and that's going to be where we encounter our distributed load. For now, let's just call this a W right there. We know the origin of our coordinate system is going to go at the location of 0 slope and the lowest spot. So maybe about right there on my picture. So X and Y. So the origin. Oh, and let's, before we put some text down below here, let's label that distance. L from A to B will be the total distance across there. And now let's note here that the origin of the coordinate system will always go at the lowest point where the slope of the cable is equal to 0. Let's get some of this geometry, other geometry on here. Our vertical distance from that low point to B we'll call YB. The horizontal distance from the lowest point to B we'll call XB. And then over here at A, we will have YA and XA. I'm going to call that lowest point on the cable point C. And then also, like I mentioned before, when the supports are at the same elevation, when YA is equal to YB, we know that XA is equal to XB is equal to L over 2. Right, it's going to be right in the middle, which is a huge advantage. If we know that, we know our geometry. We don't have to solve for our geometry. But like in this problem here, we don't know that. And so one of the first things we're going to have to figure out is, where is that low point located? What is XB? What is XA? And actually, we're going to derive our equations using an FBD of CD. Now, this C to D, point D, I'm going to come a distance to the right of point C. And that distance is going to be an arbitrary distance X. So right here. So C to D. That means our isolated system, we're going to cut through D, we're going to cut through the distributed load, we're going to cut through C, cut through distributed load. So that's going to be our FBD that we are going to draw. That distance X is just like the distance X when we did shear and moment. So it's at a distance X, we can plug in values for X, we can come up with equations for things. Our FBD then is going to have a 0 slope down here, and then it's going to increase in slope up to there. That spot right there, though, that is TD. naught. That's our minimum tension. So we're going to call T naught. That's going to be our min tension. And that's at point C. At point D, we're going to have some T as a function of X, because it's going to depend on how far that cut X is. We will also have an unknown theta there as well. That's going to be theta as a function of X. It'll change for every distance X that we get. Let's show on here our coordinate system here. There's X is right there. Y is right there, which would mean that the distance from there to there, we're going to be X, and there to there, that is going to be a distance of Y. We also have our distributed load that's acting over this. So we have a distributed load that goes from there to there, some W. If we think about X and Y as being things that we plug in a value of X and a value of Y, then how many unknowns do we really have in this FBD? We have T naught, we have T of X and theta of X. So we really have three unknowns. If we think about X and Y as kind of being a parameter that we'll plug in values for later, which means that we can solve for these three, or we can come up with the relationships for these three by using our equilibrium equations. Let's start with the moment equation. And where do you think would be good to sum moments at to reduce the number of unknowns in our equation? Where can we sum moments at? And let me put the points on there. So point C is at the low spot right here. Point D is up here. Reed, what do you think? Is Reed your name? Did I get that right? No. Oh, sorry. What is it? Dean. Dean. Okay. Sorry. I had the R or the D. Sorry. I had something. Dean. Sorry, Dean. Where do you think, Dean? D. Yeah. At D, because we get rid of T of X and we get rid of theta. So let's sum moments about point D equals 0. We've got positive going counterclockwise. A little bit interesting to sum moments about for cables, because cables don't hold any moment, but we can still say, hey, I want that, make sure that nothing is rotating in my FBD. We can still meet equilibrium for rotation. So if I sum moments about D, let's see, we're going to have a T naught, which is going to be negative. The distance to T naught is Y. We have to incorporate W. Isn't W, we're going to need to resolve into a concentrated force. So we're going to have some concentrated force there. What's that going to be equal to? W times X. So W times X right there. And where will that be located relative to point D? At X over 2. So now we can take into account a positive W times X over 2. And that all has to be equal to 0 because that's everything that's causing a moment. Now we actually can rearrange this a couple of different ways. Let's rearrange it for Y. If we rearrange this for Y, we're going to find that Y is equal to WX squared over 2T naught. that's one of our equations from our learning objectives. And that's a pretty nice looking equation, isn't it? It's this nice quadratic equation, x squared. It is actually the shape of the cable. If we plugged in a value for x, we would get the corresponding value for y at that location on the cable. And we use the moment equation to come up with that shape of our cable. So this really is the shape of the cable. The other thing we can do with this is we can also rearrange it for T naught. So that same equation, same moment equation for T naught, we're going to end up with T naught is equal to WX squared over 2Y, which is actually a nice way if we have the X and Y coordinate somewhere on our cable, like if I knew XB and YB, I could plug it in to right here and it would tell me what T naught is. So any point on our cable, we could figure out T naught, which that means if we have the same elevation, right? If XA and XB are equal to L over 2, then actually it's pretty easy for us to find T naught with that equation right there. However, if we don't, like in this one, we got to do a little bit more work in order to find what T naught is, because we got to find the location of that low point of the cable first. So we can rearrange for T naught there. The other thing that we can do with this is actually combine our sum of forces in the X and sum of forces in the Y. And we're going to do that with a force triangle. A force triangle simultaneously incorporates sum of forces in the X and sum of forces in the Y. We could do sum of force in the X, we could do sum of force in the Y. Our equations just wouldn't be as pretty. They wouldn't be as nice. We have three forces that are acting in that FBD. If we draw them as a triangle, we will have a T naught, it's horizontal going that way, a W times X that's going vertical, and a T as a function of X. And in order to meet equilibrium, they have to make a triangle where the starting and ending point are basically the same spot. So no matter where we started, right? We started here, we could follow the triangle back around. If we started here, we could follow the triangle back around to that same spot, basically doing sum of force in the X and the Y simultaneously at the same time. This angle right here would be theta as a function of X. And now we can get some nice equations like T of X using the Pythagorean theorem would just be equal to WX quantity squared plus T naught squared. Or theta of X would be equal to the inverse tangent of the opposite WX over the adjacent T naught. So now we have these equations here and this one and that one. Which we can use in place of FBDs. We actually can just go right in and say, okay, I'm just going to use the equations. I'm just going to use these relationships to solve our problems without even doing any of these FBDs. Any questions? All right, we have our three other FBDs too. that can come in handy at times. We can do the FBD of the whole. The FBD of the whole will include an AX and an AY, a BX and a BY. Notice they're all going away from the cable. They're all in tension. We would have a W times L on there, and it would be located at a distance of L over 2 and L over 2. So we can use that FBD. Sometimes the FBD of the whole thing can be very handy. And then the other one that we can have is an FBD to the left of the low point. That one would include T naught. It would include AX and AY. It would include a W times XA. And that would be located exactly halfway, so XA over 2. Or we could do an FBD to the right of the low point. That one would include a BX and a BY. Also exposes T naught, WXB at a location of XB over 2. This one will give us that y is equal to wx squared over 2t naught, actually. This one will too. If we sum moment at A or some moments at B, we're going to get that same relationship that we got in our first FBD from C to D. This one will provide us some new relationships if we needed to use that one. Usually, if we're using the equations, we don't need to use the FBDs in addition. Also, on all of these FBDs, instead of writing this as like an AX and an AY, you could also write this as a TA at an unknown theta A. So you can do that over here. We could do the same thing. Could have called it a TB at an unknown theta B. So I like the BX and the BY, but there may be times like if you know the tension at A, maybe you want to leave it as the tension, you want to draw it as a TA and a theta A. It's two unknowns in both cases, right? AX and AY or TA and a theta A. Those are both two unknowns. Okay, let's jump into an example. We have here a cable support over here at point A. And then the cable curves down like this, goes through the low point. Oh, it needs to go lower than that because this is, let's have it come lower, steeper and lower. And then it's going to come back up to a point over here. Let's draw our origin of our coordinate system here. X and Y. We'll call this point A. This will be point B. We have a distributed load. Let's see, our W is equal to 100 pounds per foot. The total length from here to here is 40 feet. The vertical distances are given. The distance over to A is 40 feet, and the distance to B is 20 feet. So they give us those two vertical distances. We do not know, however, XA or XB. Those are both unknown. They want us to find for this problem T naught and T max. For the solution, let's go ahead and let's use our equations, which is we know y is equal to wx squared over 2 T naught. And what we'll do is we're going to have equation 1. Equation 1 is going to be using the fact that we know at A, y is 40 feet, and then we have a w times xa squared over 2 T naught. So we're basically implementing that equation at the two locations where we know y. Equation 2 is going to be 20 is equal to wxb squared over 2 T naught. If we used the FBD to the low point and to the left and low point to the right, we would actually get these exact same two equations. So using our FBD, we're using the equation approach. Using the FBD approach, so if we go back over here, if we look at those two FBDs, the one to the low point, and here, if we did the sum of the moments about A, wouldn't we get WXA and T naught in our equation? We would get that equation. And then if we did the moment about B, we would get WXB. So we would get those same two equations by using those FBDs. Right now, though, I have two equations, but how many unknowns? We have XA is unknown, XB is unknown, and then there's one more. What's our third unknown? T naught. We know W is 100 pounds per foot. I just didn't plug it in. So we have 3 unknowns, but only 2 equations. Can we say something else to have a third equation? Yeah. See.
XA plus XB must be 40.
That's right. We know that the entire distance across there has to be 40. So we're going to say for equation 3 that XA plus XB has to be equal to 40 feet. Now we have 3 equations and 3 unknowns. It's a difficult system of equations to solve. And one way that I found is a nice way to handle this system of equations is to actually, I'm going to take equation 1 divided by equation 2. So 40 equals WXA squared over 2T naught divided by 20 equals WXB squared over 2T naught. What that does is it gets rid of some stuff. It gets rid of W, it gets rid of the 2T naught. So I'm left with 2 is equal to XA squared over XB squared. So really simplified things down nicely. If I rearrange this, it's basically 2XB squared minus XA squared is equal to 0. Now I can plug in into XB. Let's get XB is equal to 40 minus XA. And so we're going to end up with 2 times 40 minus XA squared minus XA squared is equal to 0. We've got a quadratic equation here. We could use the quadratic formula. We could use calculators. I used Wolfram. I wouldn't expect you all to do this on an exam because I don't want to disadvantage the people that don't have solvers on their calculator. So don't expect this on exam, but on the homework, you got to be able to figure out a way to solve this right here. And when I did Wolfram, I found actually 2 values for XA. I found XA was 136.5 and 23.43. Yes.
Why didn't back when you had 2 equal to AX squared divided by BX squared, why don't you take the square on the outside and then just make it square root 2 so you don't have to use a solve function and then you can just not have to deal with it in squares.
I don't think you can take the square root. Can you do that when it's the square root of? Is XA over XB squared the same thing as X squared over XB squared? It is? Okay, so you could do that too then. I haven't tried it, but it sounds like it should work. Okay, so I got 136.5 or 23.43. This one is out of range. So this is our actual value. It's within 40 feet. So that is XA. I'm going to use that one. Now we have XA is equal to 23.43. We can now solve for T naught. T naught is equal to W times XA squared over 2 times YA. So that's going to be 100 times 23.43 squared divided by 2 times 40. We're going to find that T naught is equal to 686.08 pounds. And then where is T max? We got to find T max. Where is T max? At A or B or C? At A, at the steepest slope, at the highest point. So we know that T max is at TA, which is going to be equal to the square root of 100 times XA squared plus T naught squared. And we are going to get, when we do that, we are going to get here 2,440 pounds. It does work?
Yeah.
Okay, awesome. Makes it a lot easier, huh? Cool. I had never thought of that. I don't know why. So thank you. All right, you all have a great rest of your Monday. We'll see you on